Welcome back to COSC 2325. In this video, I want to show you the Chapter 3 example and walk us through it. So Chapter 3 example is in Chapter 3 modules. Make sure you download the example, and then you're going to create a new project. So we're going to go to create a new project, empty project. And then we'll call this chapter example. And I'm putting it, make sure you put it wherever, whatever location you want to keep all your files in. So I'm going to go ahead and build my dependencies. Make sure I've got MASM checked off. It's okay. Then I'm going to add So here, when I build my dependencies, make sure that I check them, that they're good. And then here at the very top, make sure that this is set at the 86 processor. Okay, so at this point, I want to add an existing item. It's on my desktop, and it's called Chapter 3 Examples. I'm going to open the source file. In this source file, the first thing that I have is a symbolic constant that can be redefined. So like we studied, we talked about symbolic constants, how it's just count is just a symbol that represents the number 10. So count does not get a memory location. It's just like if you said move 10 into EAX, 10 is just a constant value. Now, it can be redefined. What that means is later on in my program, I can say count equals 20, so I can change count at any point. Then we have a symbolic constant that cannot be redefined, and we do that by using the directive EQU. I have 3 different ways to show you this directive. So I have using the less than and greater than signs with an expression inside it. So this is an expression, but if you put this expression with the less than and greater than sign surrounding it, it now becomes a text expression. And it doesn't mean that it's a string, it acts like a macro. So anytime that you say num1, you are going to get 5 times 5. So you will get the 25 in decimal. If you put that into a register, you'll see it as a hex. So this gives you 25 and this gives you 25, except this will be first calculated, and num2 will be a constant 25, and then this is calculated whenever num1 gets assigned to something or gets used. Okay, this here is again is a constant, but this time in the less than and greater than signs, we're seeing a string, and this is a null terminated string. Each one of these characters is 1 byte. Each of these is 32 bytes. Then here we have, we're using text EQ directive, and with this directive, we can create macros and they can be redefined. So anytime that you use this label, set up AL label in your program, it will act like this instruction, and it will move 10 into this register, which is what I've done here. So here at this point, you'll see 10 gets moved to AO. 10 to AO. And we'll look at it in a minute. Then here, num1 and num2, we said we're 25. So here, 25 gets moved to EAX, and here 25 gets moved to EBX. Okay. We'll look at these in the middle in just a second, but let's look at val1 and val2. So val1 is a double word, so it's a 32-bit hex value that contains 1, 2, 3, 4, 5, 6, 7, 8. So you'll see this number in val1, and you'll see this number, hex number, in val2. Now, in the register, you'll see 1, 2, 3, 4, 5, 6, 7, 8. If you look at val1 in memory, val1 in memory will be in little Indian order. Little Indian order. So what you're going to see is going to be in memory, you'll see this first byte, 7, 8. The first byte will be 7, 8. The second byte will be 5, 6. And then 3, 4. And then 12. Because for the Intel 86 processor, anything that is saved in memory, any values, integer values that are saved in memory are going to be in little Indian order. This will also be in little Indian order, so this will be 43, 85, 96, 70 saved in val2, but then once we get that from val1 and val2 and we extract it, so when the CPU extracts that from memory, it takes it out and puts it in the correct order in EAX. So EAX will contain, it's 1, 2, 3, 4, 5, 6, 7, 8 hex, and EBX, and then EAX it's changed to val2, which is 7, 8, 9, 6, 8, 5, 4, 3 hex. 7, 8, 9, 6, 5. I think I put 5 too many times. 7, 8, 9, 7, 8, 9, 6, 8, 5, 4, 3. Okay, so this number EX will get changed. So I'm going to go ahead and put my breakpoint at setup AL, and we're just going to see these instructions, and then we'll get back to the erase. I'm going to run my program, and I see right here, I have my memory window. If you don't see your memory window, remember you run it in debug. You got to be in debug. So you got to see this little stop debug. Then you got to go to debug windows, click on register so you can see the registers, and click on memory 1 so you can see the memory window. So here, if I put and sign, and I want to see what is in val1. Okay, so val1 in memory, this is the address of val1. This is where it's found, and notice that it's in little Indian order. So 7, 8, 5, 6, 3, 4, 1, 2. And then directly after is going to be this number in little Indian number 4, 3, 8, 5, 9, 6, 7, 8, because val2 is in memory is going to be the very next. This is double word. So after 4 bytes, then we'll see val2. Okay. So here I can also look at this. This is 1 byte integers. I can look at this as 4 byte integers. So I can see the whole number. If I look at them as 4 bytes, but if I look at them as 1 byte integers, then I'll see the little Indian order. Then if I look at the registers, and I step through setup AL, then AL is in the EAX register, is the lowest byte, and it gets a 10, and 10 in hex is A. And if I step over that, num1 gets moved to EAX. So EAX now has 19 hex. 19 hex is 25 decimal. And if I move through this again, then 19 is hex is moved to EBX because 25 decimal is 19 hex. Then val1 is going to get moved to EAX. So val1, it has 1, 2, 3, 4, 5, 6, 7, 8. And then val2 is moved to EAX, and I stopped the program. Sorry about that. But you can run it, and you can see that val2 will then, this number will go into EAX. Okay, what I want to look at next is this array here. So this array, if I run the program, and I look at my memory window, and I type in array 1, so the address of array 1. This is my memory segment. My data segment begins at array 1. So I'm going to get to see everything that is in, everything that gets memory space, that gets assigned in memory space. So here, my array 1 has 10 bytes that each one contains a 1. So there's a 1, a 1, a 1, a 1, a 1. There's 10 of these. Because I say duplicate 1, so give me 10 elements with a 1 in it. And each one is 1 byte. This here gives me the size, the length of the array, like how many values are in the array. Well, the array has 10 elements, and this here will give me 10. We'll go back to that in a second. But that does, this array size, because it uses the equal sign, does not get a memory location. So the next thing that I see right after these ones is the name Jeanette. And I'm seeing the name Jeanette in hex. So G is in hex is 47. You can go look at the ASCII table and verify that lowercase I in hex is 69. This is GINNETTE, null termination. Then here's my val1 in the little Indian order, 7, 8, 5, 6, 3, 4, 12. And then my val2 contains 4, 3, 8, 5. And it's, so these are all adjacent to each other, okay, in memory. So what that means is this right here, the way that this works is the $sign, what it does is it gives you the current location of the current, the current address of the current instruction. So it gives you the current address, the current instruction, and then it subtracts array 1. It subtracts where array 1 begins. Well, array 1 begins at offset 0, 0. And array size, so array 1 takes, because it's a byte, okay, it means that we're using 10 bytes from 0 to 9. So the next instruction is at the 10th byte. And so 10 minus 0 gives me 10, which gives me the size of the array because it has 10 elements. Now, if this was a word size array, then word is 2 bytes. So 2 times 10 would be 20. So this location would be 20, 20 minus 10. Sorry, 20 minus 0, because array 1 begins in 0, so 20 minus 0 would be 20, and I would have to divide by 2 to give me my size, my length, which is 10. And that's how this works. So this gives you the current, you got to have this instruction right under the array, otherwise, because the $sign gives you the offset, the address of the current instruction, okay, which is going to be right after the arrays defined. Okay, so we're going to stop this, and the next thing I want to show you is how to create a listing file and take a look at that listing file. So you're going to right click on the name of the project and go to properties and open Microsoft macro assembler. Click on that so you can see what's in it, and click on listing file. And this is in your book also, so you can always go back to your book. You're gonna right click here on the right and choose yes from the drop down menu. List all available information. We're gonna say yes to that. Here where it says enable assembly general code listing, we're gonna also choose yes. And then down here where it says listing file, symbol code listing file, click on that, click edit. You're going to type $, open parentheses, project name. What this does, what project name does is it gives you whatever name you named this. Okay. So notice when I close that parentheses, automatically it gives me chapter 3 example because that's what I called my project. Then we're going to put .lst. That's going to be the extension of your file. That's how you're going to find your file. The listing file is going to be called chapter 3 example.lst. Press OK. Press apply. And OK. Now, when I run my program, I'm going to take out this here. By the way, once you do that, you're not going to be able to go back into debug mode. So you'll have to take all that off of the listing to be able to do debug again, okay? So now I'm going to run the program. Close my console window. And I'm going to open this listing file. So when I go to open file, I've got to go to the folder where your source file is kept. Mine is here. You want me to open it up? Let's show it. So let's open. File. Should be right here. Oh, here we go. So I need to click on chapter 3 example, and then here's my listing file. Okay, so when the assembler takes your program and takes your source file and assembles a source file, it creates this listing file for you if you set it up to show it to you. And in this listing file, you can see, this is the start of my program, there's some comments. So right here, here's this symbolic constant that we defined, count equals 10. And it doesn't get assigned an address. Now I know that because if I look down here where I have these move instructions, This is the address where this move instruction starts. This is the address where this move instruction starts. So this doesn't have that. All this has is the value of count. Count is 10. There's 10 right there. Again, this does not get an address. This is 5 times 5. This is hex 19. So these are the actual values, and they don't get an address. Here's my macro. So we start here. This is where the program begins, and the first thing to get an address is array 1. Array 1 gets this address. And then, and actually like the 000 here actually gets added to the address of where this program begins. So this instruction here is at address 00 offset 0000. And this next instruction actually does not get an address, but this instruction does. And this instruction goes from 0 to 9. So this one starts at 10, which is A. And then we have Jeanette. Here, null terminated. If we look down here in the code section, we have this instruction. And these right here are called upcodes, B8, BB, A1. These are called upcodes. And for example, I know that this A1 upcode means that you're moving a 32-bit integer into a 32-bit memory location, actually, not just an integer, but 32 memory location into EAX register. That is what A1 means. 32-bit mem. Okay, so mem32 into an EAX. I don't know these exactly what B8 upcode means in BB, but they would mean something specific. It's getting moved into EAX. We can go into any search engine and find out what the upcodes are. So this here's the address where the instruction begins. This is moving 19 into EAX, 19 into EBX. This is moving, let's see, 13 into A1 and 17 into A1. And I'm not sure what these R's mean, but we can also look that up and see what they mean. So this is just what your listing file looks like, and here's some more information. So if you want to, we're not going to be, you're not going to be tested over listing files. You're not going to be having to look at listing files and be able to tell what's in them, but it's just interesting to look to see what gets